But we're going to do a Python code doing text classification, very popular for doing the naive Bayes. So we're going to use our new tool to perform a text classification of news headlines and classify news into different topics for a news website. As you can see here, we have a nice image of the Google News, and then related on the right, subgroups. I'm not sure where they actually pulled the actual data we're going to use from. It's one of the standard sets. But certainly this can be used on any of our news headlines in classification. So let's see how it can be done using the naive Bayes classifier. Now we're at my favorite part. We're actually going to write some Python script. Roll up our sleeves. And we're going to start by doing our imports. These are very basic imports, including our news group. And we'll take a quick glance at the target names. Then we're going to go ahead and start training our data set and putting it together. We'll put together a nice graph, because it's always good to have a graph to show what's going on. And once we've trained it and we've shown you a graph of what's going on, then we're going to explore how to use it and see what that looks like. Now, I'm going to open up my favorite editor or inline editor for Python. You don't have to use this. You can use whatever your editor that you like, whatever interface IDE you want. This just happens to be the Anaconda Jupyter Notebook. And I'm going to paste that first piece of code in here so we can walk through it. Let's make it a little bigger on the screen so you have a nice view of what's going on. And we're using Python 3, in this case 3.5. So this would work in any of your 3x. If you have it set up correctly, it should also work in a lot of the 2x. You just have to make sure all of the versions of the modules match your Python version. And in here, you'll notice the first line is your percentage matplotlib library in line. Now, 3 of these lines of code are all about plotting the graph. This one lets the notebook know, since this is an inline setup, that we want the graphs to show up on this page. Without it in a notebook like this, which is an Explorer interface, it won't show up. Now, a lot of IDEs don't require that. A lot of them, like if I'm working on one of my other setups, it just has a pop-up and the graph pops up on there. So you have that setup also. But for this, we want the matplotlib library in line. And then we're going to import NumPy as NP. That's NumberPython, which has a lot of different formulas in it that we use for both of our sklearn module. And we also use it for any of the upper math functions in Python. And it's very common to see that as NP, NumPy as NP. The next 2 lines are all about our graphing. Remember I said 3 of these were about graphing? Well, we need our matplotlib.pyplot as PLT. And you'll see that PLT is a very common setup, as is the SNS, and just like the NP. And we're going to import Seaborn as SNS, and we're going to do the SNS.set. Now, Seaborn sits on top of PyPlot, and it just makes a really nice heat map. It's really good for heat maps. And if you're not familiar with heat maps, that just means we give it a color scale. The term comes from the brighter red it is, the hotter it is in some form of data, and you can set it to whatever you want. And we'll see that later on. So you'll see that those 3 lines of code here are just importing the graph function so we can graph it. And as a data scientist, you always want to graph your data and have some kind of visual. It's really hard just to shove numbers in front of people and they look at it and it doesn't mean anything. And then from the sklearn.datasets, we're going to import the fetch 20 news groups. Very common one for analyzing, tokenizing words and setting them up and exploring how the words work and how do you categorize different things when you're dealing with documents. And then we set our data equal to fetch 20 news groups. So our data variable will have the data in it. And we're going to go ahead and just print the target names, data.targetNames. And let's see what that looks like. And you'll see here we have alt atheism, comp graphics, comp OS, MS, Windows.miscellaneous. And it goes all the way down to talkpolitics.miscellaneous, talkreligion.miscellaneous. These are the categories they've already assigned to this news group. And it's called Fetch 20 because you'll see I believe there's 20 different topics in here, or 20 different categories as we scroll down. Now, we've gone through the 20 different categories, and we're going to go ahead and start defining all the categories and set up our data. So we're actually going to go ahead and get the data all set up and take a look at our data. And let's move this over to our Jupyter Notebook. And let's see what this code does. First, we're going to set our categories. Now, if you noticed up here, I could have just as easily set this equal to data.target underscore names, because it's the same thing. But we want to kind of spell it out for you so you can see the different categories. It kind of makes it more visual so you can see what your data is looking like in the background. Once we've created the categories, we're going to open up a train set. So this training set of data is going to go into fetch 20 news groups, and it's a subset in there called train, and categories equals categories. So we're pulling out those categories that match. And then if you have a train set, you should also have the testing set. We have test equals fetch 20 news groups, subset equals test, and categories equals categories. Let's go down one size so it all fits on my screen. There we go. And just so we can really see what's going on, let's see what happens when we print out one part of that data. So it creates train, and under train it creates train.data, and we're just going to look at data piece number 5. And let's go ahead and run that and see what that looks like. And you can see when I print train.data number 5 under train, it prints out one of the articles. This is article number 5. You can go through and read it on there. And we can also go in here and change this to test, which should look identical because it's splitting the data up into different groups, train and test. And we'll see test number 5 is a different article, but it's another article in here. And maybe you're curious and you want to see just how many articles are in here. We could do length of train.data. And if we run that, you'll see that the training data has 11,314 articles. So we're not going to go through all those articles. That's a lot of articles. But we can look at one of them just so you can see what kind of information is coming out of it and what we're looking at. And we'll just look at number 5 for today. And here we have it. Rewording the Second Amendment IDs, VTT, line 58, lines 58, in article, etc. And you can scroll all the way down and see all the different parts to there. Now, we've looked at it, and that's pretty complicated when you look at one of these articles to try to figure out how do you weight this. If you look down here, we have different words, and maybe the word from. Well, from is probably in all the articles, so it's not going to have a lot of meaning as far as trying to figure out whether this article fits one of the categories or not. So trying to figure out which category it fits in based on these words is where the challenge comes in. Now that we've viewed our data, we're going to dive in and do the actual predictions. This is the actual naive Bayes. And we're going to throw another model at you, or another module at you here in just a second. We can't go into too much detail, but it deals specifically working with words and text and what they call tokenizing those words. So let's take this code and let's skip on over to our Jupyter Notebook and walk through it. And here we are in our Jupyter Notebook. Let's paste that in there. And I can run this code right off the bat. It's not actually going to display anything yet, but it has a lot going on in here. So at the top we had the print module from the earlier one. I didn't know why that was in there. So we're going to start by importing our necessary packages. And from the sklearn features extraction .text, we're going to import tf-idf vectorizer. I told you we're going to throw a module at you. We can't go too much into the math behind this or how it works. You can look it up. The notation for the math is usually tf.idf. And that's just a way of weighing the words. And it weighs the words based on how many times they're used in a document, how many times or how many documents they're used in. And it's a well-used formula. It's been around for a while. It's a little confusing to put this in here, but let's let it know that it just goes in there and weights the different words in the document for us. That way we don't have to wait. And if you put a weight on it, if you remember I was talking about that up here earlier, if these are all emails, they probably all have the word from in them. From probably has a very low weight. It has very little value in telling you what this document's about. Same with words like in article, in articles, in, cost of, un, maybe cost might, or where words like criminal, weapons, destruction, these might have a heavier weight because they describe a little bit more what the article's doing. Well, how do you figure out all those weights in the different articles? That's what this module does. That's what the tf-idf vectorizer is going to do for us. And then we're going to import our sklearn.naive Bayes, and that's our multinomial NB. Multinomial naive Bayes. Pretty easy to understand that, where that comes from. And then finally we have the sklearn pipeline import make pipeline. Now the make pipeline is just a cool piece of code because we're going to take the information we get from the tf-idf vectorizer and we're going to pump that into the multinomial in B. So a pipeline is just a way of organizing how things flow. It's used commonly. You probably already guessed what it is if you've done any businesses. They talk about the sales pipeline. If you're on a work crew or a project manager, you have your pipeline of information that's going through, or your projects and what has to be done in what order. That's all this pipeline is. We're going to take the TF-ID vectorizer and then we're going to push that into the multinomial in B. Now, we've designated that as the variable model. We have our pipeline model. And we're going to take that model, and this is just so elegant. This is done in just a couple lines of code. Model.fit. And we're going to fit the data, and first the train data, and then the train target. Now, the train data has the different articles in it. You can see the one we were just looking at. And the train.target is what category they already categorized that particular article as. And what's happening here is the train data is going into the TF-ID vectorizer. So when you have one of these articles, it goes in there, it weights all the words in there. So there's thousands of words with different weights on them. I remember once running a model on this, and I literally had 2.4 million tokens go into this. So when you're dealing like large document bases, you can have a huge number of different words. It then takes those words, gives them a weight, and then based on that weight, based on the words and the weights, and then puts that into the multinomial in B. And once we go into our naive Bayes, we want to put the train target in there. So the train data that's been mapped to the TF-ID vectorizer is now going through the multinomial in B, and then we're telling it, well, these are the answers. These are the answers to the different documents. So this document that has all these words with these different weights from the first part is going to be whatever category it comes out of. Maybe it's the talk show or the article on religion, miscellaneous. Once we fit that model, we can then take labels, and we're going to set that equal to model.predict. Most of the sklearn use the term .predict to let us know that we've now trained the model and now we want to get some answers. And we're going to put our test data in there because our test data is the stuff we held off to the side. We didn't train it on there and we don't know what's going to come up out of it, and we just want to find out how good our labels are. Do they match what they should be? Now, I've already run this through. There's no actual output to it to show. This is just setting it all up. This is just training our model, creating the labels so we can see how good it is, and then we move on to the next step to find out what happened. To do this, we're going to go ahead and create a confusion matrix and a heat map. So the confusion matrix, which is confusing just by its very name, is basically going to ask how confused is our answer. Did it get it correct, or did it miss some things in there or have some missed labels? And then we're going to put that on a heat map so we'll have some nice colors to look at to see how that plots out. Let's go ahead and take this code and see how that, take a walk through it and see what that looks like. So back to our Jupyter notebook, I'm going to put the code in there, and let's go ahead and run that code. Take it just a moment. And remember, we had the inline, that way my graph shows up on the inline here. And let's walk through the code and then we'll look at this and see what that means. So, make it a little bit bigger. There we go. No reason not to use the whole screen. Too big. So we have here from sklearn metrics import confusion matrix. And that's just going to generate a set of data that says the prediction was such, the actual truth was either agreed with it or is something different. And it's going to add up those numbers so we can take a look and just see how well it worked. And we're going to set a variable mat equal to confusion matrix. And we have our test target, our test data that was not part of the training. Very important in data science, we always keep our test data separate. Otherwise, it's not a valid model if we can't properly test it with new data. And this is the labels we created from that test data. These are the ones that we predict it's going to be. So we go in and we create our SN heat map. The SNS is our seaborn, which sits on top of the pie plot. So when we create a SNS.heatmap, we take our confusion matrix, and it's going to be mat.t. And do we have other variables that go into the SNS.heatmap? We're not going to go into detail what all the variables mean. The annotation equals true. That's what tells it to put the numbers here. So you have the 166, the 1, the 0001. Format D and C bar equals false have to do with the format. If you take those out, you'll see that some things disappear. And then the X tick labels and the Y tick labels, those are our target names. And you can see right here, that's the alt atheism, comp graphics, comp OS, MS Windows, miscellaneous. And then finally, we have our plt.x label. Remember, the SNS or the Seaborn sits on top of our matplot library, our PLT. And so we want to just tell it x label equals a true is true. The labels are true, and then the y label is prediction label. So when we say a true, this is what it actually is, and the prediction is what we predicted. And let's look at this graph, because that's probably a little confusing the way I rattled through it. And what I'm going to do is I'm going to go ahead and flip back to the slides, because they have a black background they put in there that helps it shine a little bit better so you can see the graph a little bit easier. So in reading this graph, what we want to look at is how the color scheme has come out. And you'll see a line right down the middle, diagonally, from upper left to bottom right. What that is if you look at the labels, we have our predicted label on the left and our true label on the right. Those are the numbers where the prediction and the true come together. And this is what we want to see, is we want to see those lit up. That's what that heat map does, is you can see that it did a good job of finding those data. And you'll notice that there's a couple of red spots on there where it missed. You know, it's a little confused when we talk about talk religion miscellaneous versus talk politics miscellaneous, social religion Christian versus alt atheism. It mislabeled some of those. And those are very similar topics, so you could understand why it might mislabel them. But overall, it did a pretty good job. If we're going to create these models, we want to go ahead and be able to use them. So let's see what that looks like. To do this, let's go ahead and create a definition, a function to run. And we're going to call this function, let me just expand that just a notch here. There we go. I like mine in big letters. Predict categories. We want to predict the category. We're going to send it S, a string. And then we're sending it train equals train. We have our training model. And then we had our pipeline, model equals model. This way we don't have to resend these variables each time. The definition knows that because I said train equals train, and I put the equal for model. And then we're going to set the prediction equal to the model.predictS. So it's going to send whatever string we send to it. It's going to push that string through the pipeline, the model pipeline. It's going to go through and tokenize it and put it through the TF, IDF, convert that into numbers and weights for all the different documents and words. And then it'll put that through our naive Bayes. And from it, we'll go ahead and get our prediction. We're going to predict what value it is. And so we're going to return train.targetNamesPredict of 0. And remember that the train.targetNames, that's just categories. I could have just as easily put categories in there, .predict of 0. So we're taking the prediction, which is a number, and we're converting it to an actual category. We're converting it from, I don't know what the actual numbers are, but let's say 0 equals alt atheism. So we're going to convert that 0 to the word. Or 1, maybe it equals comp graphics. So we're going to convert number 1 into comp graphics. That's all that is. And then we got to go ahead and then we need to go ahead and run this. So I load that up. And then once I run that, we can start doing some predictions. I'm going to go ahead and type in predict category. And let's just do predict category Jesus Christ. And it comes back and says it's social, religion, Christian. That's pretty good. Now note I didn't put print on this. One of the nice things about the Jupyter Notebook Editor and a lot of inline editors is if you just put the name of the variable out as returning the variable train.target_names, it'll automatically print that for you. In your own IDE, you might have to put in print. Let's see where else we can take this. And maybe you're a space science buff. So how about sending load to International Space Station? And if we run that, we get science space. Or maybe you're a automobile buff. And let's do, they were going to tell me Audi is better than BMW, but I'm going to do BMW is better than an Audi. So maybe you're a car buff. And we run that, and you'll see it says recreational. I'm assuming that's what REC stands for. Autos. So I did a pretty good job labeling that one. How about if we have something like a caption running through there? President of India. And if we run that, it comes up and says talk, politics, miscellaneous. So when we take our definition or our function and we run all these things through, kudos, we made it. We were able to correctly classify texts into different groups based on which category they belong to using the naive Bayes classifier. Now, we did throw in the pipeline, the TF-IDF vectorizer, we threw in the graphs. Those are all things that you don't necessarily have to know to understand the naive Bayes setup or classifier. But they're important to know. One of the main uses for the naive Bayes is with the TF-IDF tokenizer or vectorizer, where it tokenizes the word and adds labels. And we use the pipeline because you need to push all that data through, and it makes it really easy and fast. You don't have to know those to understand naive Bayes, but they certainly help for understanding the industry and data science. And we can see our categorizer, our naive Bayes classifier. We were able to predict the category religion, space, motorcycles, autos, politics, and properly classify all these different things we pushed into our prediction and our trained model. Let's go ahead and wrap it up, and let's just go through what we covered. We gave you an introduction to naive Bayes and how it's used to perform basic classification as a classifier. We went through the basic formula, the probability of A given B and the probability of B given A, the basics of the naive Bayes. We touched a little bit on some of the different uses for the naive Bayes. We also went over the advantages of it and where it really shines, especially when we talk about real-time processing. Naive Bayes is very fast.
이전 참고 동영상에서 다뤘던 나이브 베이즈를 간단히 요약해 보도록 하겠습니다. Bayes classifier는 probabilistic framework for solving classification problem, 분류 문제를 풀기 위한 확률적 프레임워크입니다. Conditional probability는 py given x는 pxy를 px로 나눈 것입니다. 또한 px given y는 pxy를 py로 나눈 것입니다. Bayes theorem은 py given x는 px given y에 py를 곱한 뒤 px로 나눈 것입니다. 분류기가 반드시 가져야 되는 속성은 attribute x가 주어졌을 때 클래스 y를 예측할 수 있어야 되는 것입니다. py given x는 그런 조건을 만족합니다. px given y와 py는 훈련 데이터에서 얻을 수 있습니다. px는 모든 베이스 티어렘의 공통적이기 때문에 굳이 계산을 할 필요가 없습니다. 이에 대해서 좀 더 자세히 알아보도록 하겠습니다. Using Bayes theorem for classification. Bayes theorem을 classification을 위해서 사용하는 방법입니다. Consider each attribute and class label as random variable. 먼저 각각의 attribute와 클래스는 random variable로 가정합니다. Given a record with attribute x1, x2, xd. 오른쪽 테이블에 보이는 것처럼 attribute는 refund, marital status, taxable income 등이 있습니다. Goal is to predict class Y. 목표는 class Y, 즉 evade를 예측하는 것입니다. Specifically, we want to find the value of Y that maximizes PY given X. 다음 단계로 PY given X를 데이터로부터 구하는 방법을 알아보도록 하겠습니다. 다음은 테스트 레코드에서 애트리뷰트의 값들이 주어졌을 때 이에 상응하는 클래스의 확률을 구하는 것입니다. 클래스 evade는 yes와 no의 값을 가질 수 있기 때문에 우리는 p-evade equal yes given x와 p-evade equal no given x 값을 구해야 됩니다. 그 결과 probability가 더 높은 클래스 값을 예측치로 선정하게 되는 것입니다. Compute posterior probability py given x using the Bayes theorem. 베이즈 이론을 사용해서 사후 확률 py 기분 x를 계산합니다. maximum of posteriori는 py 기분 x를 최대화하는 y를 선택하는 것입니다. 이것은 px 기분 y에 py를 곱한 값을 maximize하는 y를 찾는 것과 같은 문제입니다. 다음은 px 기분 y를 에스티메이트하는 방법에 대해서 알아보도록 하겠습니다. 주어진 테스트 레코드에 대해서 attribute x 값이 주어져 있습니다. 베이즈 이론을 사용하면 클래스 이베이드가 yes 값을 가질 때는 p yes 기분 x를 계산하면 되고 no 값을 가질 때는 p no 기분 x를 계산하면 됩니다. 이 값들을 구하기 위해서는 px 기분 yes와 px 기분 no 값을 먼저 구해야 됩니다. 이 값들을 분류하기 위해서는 나이브 베이스 클래시파이어를 사용할 수 있습니다. 이 분류기의 가장 큰 특징은 attribute xi가 서로 독립적이라고 가정하는 것입니다. 그렇게 되면 우리는 pxi 기분 yj를 쉽게 계산할 수 있습니다. 나이브 베이스를 주어진 테스트 레코드 x에 적용해 보겠습니다. px 기분 yes는 p refund no 기분 yes 곱하기 p divorce 기분 yes 곱하기 p income 120k 기분 yes입니다. 클래스가 no인 경우 px 기분 no는 p refund no 기분 no 곱하기 p divorce 기분 no 곱하기 p income 120k 기분 no입니다. 이에 더하여 클래스 y의 확률을 구하면 우리는 나이브 베이스 분류기를 구현할 수 있습니다. py가 클래스 y의 확률입니다. 구체적으로는 클래스 y의 인스턴스 프랙션입니다. p no의 경우에는 7 나누기 10이 되고 p yes의 경우에는 3 나누기 10이 됩니다. 클래스 이베이드처럼 categorical attribute 경우에는 pxi equals c 기분 y는 nc 나누기 n이 됩니다. c가 no인 경우 nc는 7이 되고 c가 yes인 경우 nc는 3이 됩니다. 아래 example을 보면 p status merit 기분 no가 4 나누기 7이 되고 p refund yes 기분 yes가 0이 됩니다. 이를 다르게 표현하면 클래스가 yes일 때 refund가 yes인 경우가 한 번도 없다는 뜻입니다. continuous attribute 경우에는 discretization 이산화를 사용해서 partition the range into bins range를 여러 개의 빈들로 partition 나눕니다. replace continuous value with bin value 그 다음에 연속적인 값을 빈의 값으로 바꿉니다. probability density estimation 확률 밀도 추정에서는 특별한 정보가 없으면 attribute가 normal distribution을 따른다고 가정합니다. 이를 통해서 pxi 기분 y를 계산합니다. 통계에서 가장 기본이 되는 normal distribution입니다. 값만 대입하면 쉽게 확률을 얻을 수 있습니다. 만약 income attribute에 대해서 클래스가 no인 경우 표에서 보면 sample mean은 110이 되고 variance는 2975가 됩니다. 이를 위에 normal distribution 식에 대입하면 0.0072가 나옵니다. 우리는 이제 나이브 베이스 클래시파이어를 구현하기 위한 필요한 정보를 다 얻었습니다. 테스트 레코드가 주어졌을 때 우리는 py 기분 x를 구하기 위해서 px 기분 y와 py를 모두 구할 수 있습니다. 이를 바탕으로 p no 기분 x와 p yes 기분 x를 계산합니다. 오른쪽 아래에 보면 p no 기분 x가 py 기분 x보다 더 크다는 것을 알 수 있습니다. 따라서 클래스는 no로 분류가 됩니다. 나이브 베이스의 장단점입니다. 첫째로 robust isolated noise point 아이솔레이트된 노이즈들에 대해서 로버스트합니다. 두 번째로 handle missing values by ignoring the instance. 인스턴스를 무시함으로써 missing value를 핸들합니다. 세 번째로 관련 없는 애트리뷰트들의 로버스트합니다. 다음은 단점입니다. redundant and correlated attributes. 불필요하고 상관관계가 높은 속성들에 대해서는 will violate class conditional assumption. 클래스 조건 가정을 위배하기 때문에 분류 결과가 부정확할 수 있습니다. 이러한 경우에는 Bayesian Belief Network, 약자로 BBN 테크닉을 사용해서 문제를 해결하도록 합니다. 나이브 베이스의 단점을 초래하는 근본적 원인은 우리가 px 기분 y를 계산하기 위해서 attribute xi 간의 독립성을 가정했다는 것입니다. 이것을 통해서 트레이닝 데이터로부터 pxi 기분 yj를 쉽게 얻을 수 있기 때문에 나이브 베이스가 잘 동작했던 것인데, 만일 애트리뷰트들이 서로 correlation, 상관관계가 높다면 이 가정을 깨지는 것이고 그 결과 분류기는 잘 작동을 하지 않을 수도 있습니다. 요약하면 나이브 베이스는 애트리뷰트들이 서로 독립적일 때만 잘 동작합니다.